Assalamu alaikum. Hello everyone. In my previous two videos I discussed the properties and identification of time series. In this video I'm going to discuss some tools which are used for identification of time series, and these include autocorrelation function and partial autocorrelation function. Let me remind you that previously we discussed the visual inspection of time series to identify whether the process is stationary or not. We also learned about some processes, that is AR, MA and autoregressive moving average. We also need to identify which one in order to understand. Then eventually we will use that model for forecasting, which means that we may estimate alternative models, and we will select the best one that will be used for forecasting, and there are some tools to identify the best model. We are using autocovariance and autocorrelation, and that basically relates to the relation between observations at different legs. The autocovariance of a series at time t and time t minus 1 minus j, t minus j, is given by gamma j, and that is equal to the expected value of yt minus mu times yt minus j minus mu, where mu is the expected value of the y series. And the autocorrelation is equal to the autocovariance divided by variance of y, and that is shown by rho j. So we are using autocorrelation function, which is also known as a parallelogram, and that is the graph of autocorrelations at each leg. Let us examine our previous example of the variables, variable 1 and variable 2. The variable 1 is AR1 with the coefficient of autoregression at leg first equal to 0.7. So if that coefficient is 0.7, then the autocorrelation function is like this, and there is a geometric decay. You see that the autocorrelation, the coefficient of autocorrelation at leg 1 is equal to 0.7, then it is 0.5, and then it is 0.39, and so on. So there is a geometric decay like this. Regarding the variable 2, which is MA1, and the coefficient of the moving average at leg 1 is also equal to 0.7, but in this case there is a abrupt cutoff or drop in the autocorrelation from 0.5 to 0.08 and so on. So there is a cutoff. Now what is partial autocorrelation function? If we have this function like yt is equal to a hat plus b1 hat, yt minus 1 plus b2 hat, yt minus 2 plus bp, yt minus p plus et. Now in this case the pth partial correlation is the pth coefficient of a linear regression of yt on its legs up to p. Now this is a linear regression of yt on its own legs up to leg p. So this coefficient bp hat is the partial autocorrelation of this linear regression at leg p. So this is the autocorrelation of the pth autocorrelation, the coefficient of linear regression at pth partial autocorrelation. And this basically shows the relationship between yt and yt minus 1 controlling for the effects of other legs up to p. For example, if p is equal to 3, then we will regress yt on yt minus 1, yt minus 2, yt minus 3. Then the coefficient of yt minus 3 is the partial autocorrelation of this regression on its leg up to 3. There are some identifiable patterns for autocorrelation and partial autocorrelation function. This is the correlogram of autoregression of order 1 when the coefficient b is equal to 0.8. When this is positive, then there is a geometrical decay in the autocorrelation function like this. If this b is less than 0, then there will be oscillation of autocorrelation from negative to positive, and there is also a geometrical decay like this. So in case of negative, there will be a negative autocorrelation followed by positive, followed by negative, and followed by positive. So there will be oscillation. But in case of positive coefficient of autoregression of order 1, there is a series of autocorrelation, positive autocorrelation, and there is a geometrical decay. This is a correlogram of autoregression of order 3. In the first case, V1 is 1.4, V2 is minus 0.6, and V3 is 0.1, and there is a geometrical decay in the autocorrelation functions. When V1 is minus 0.2, V2 is 0.7, and V3 is 0.3, then in that case, this is the process how the autocorrelation coefficients tend towards 0. Here is the identifiable patterns for autocorrelation function and partial autocorrelation function. If you use partial autocorrelation function in ARP after leg P, there will be a sudden drop off. For example, in this AR1 process, when B is equal to 0.8, then the partial autocorrelation of this process will drop off suddenly, and here it is negative, but there is an abrupt drop off in the partial autocorrelation function, and this is a autoregression of order 3. B1 is equal to 1.4, B2 is equal to minus 0.6, and B3 is equal to 0.1, and this is how partial autocorrelation decays. And this is the partial autocorrelation in case of AR3, when B1 is equal to minus 0.2, B2 is equal to 0.7, and B3 is equal to 0.3. This is for MA3 process, and this is the opposite patterns for MA of order Q. There is abrupt drop off in ACF after Q, and there is gradual decay towards 0 in partial autocorrelation function. So in case of this correlogram, there is a sudden drop off or cut off, but in case of autocorrelation of moving average of order 3, there is a gradual decay towards 0 in partial autocorrelation function. Ladies and gentlemen, thank you very much for your attention. Kindly subscribe to the channel and do not forget to click on the bell icon so that you can get notification about my other videos that I will upload for you. Kindly share the channel with your students, with your friends, with your colleagues.